Section 2.3, Analyzing and Building Electrical Circuits. We're going to begin to explore how we can control electricity to meet our needs. Now, it's important to understand what electric charge is, and that a circuit is used to control electrical current. Electric charge is not necessarily used up, when electricity passes or when it goes in a circuit. It's that as a charge moves in a circuit, there is a certain kind of energy there. There is that's electrical energy. And that electrical energy is actually changed. Energy cannot be created or destroyed. It's just changed from one form of energy into another. That electrical energy is a form of kinetic energy. It's a form of movement. But it's changed into forms of energy as it's changed to heat energy. It's changed to sound. It's changed into light energy. So a charge that has gone its round, so to speak, that's finished its path in a circuit doesn't lose its charge. However, there is less energy at the end of the circuit compared to at the beginning of the circuit, but the charge is not used up. We're going to also be talking about sources of energy, and the common source of energy or voltage is battery. And we might think that batteries store electrical charges, but the electric charges that we see in a circuit, which we're going to learn about circuits, that charge comes from what the conductor is made out of. Okay, so the conductor is made up of usually it's copper, right? And we learned that everything on the periodic table of the elements are made up of atoms. So it's, for example, the atoms of copper as our main conductor contain protons, neutrons, and electrons. Well, the main component of charges in a circuit come from those electrons. Okay, and as I said, they are they're just part of the atoms that make up the copper in the conductor in the circuit. So what does a battery do? Again, a battery provides the push. A battery provides the voltage. Okay, it provides that push or that energy that is required for electrical charges to move through the circuit. Okay, so that's important to understand. A battery that is charged, right, or that is uncharged, I should say, it's that it doesn't have charge. It's a bit of a misnomer, right? It doesn't mean that the battery doesn't have any charge. What it actually means is that it doesn't have the ability to supply energy or voltage or the push, okay, to the circuit. And so if there's no push, then no charge can be, no current can flow. Okay. It's important to say before we start that electricity is used in many different ways. You use your computers, you use your laptops right now. You turn on your lights when you walk into a room. You listen to the car radio. You turn on the car to go. You use your microwave to heat food. You send text messages to a friend, right? You ride a bus to school, right? There's so many things. Okay. At home, we play video games. We turn on our ovens to cook food. We use so many different things. Based. So what I'm trying to say is that we're very, very dependent on electricity. Okay. So this section is going to teach us that how we can connect wires will determine how we can affect current because that's going to impact how current flows. Okay, so that's what we're going to talk about. All right, so this is an important distinction to make. We have a drawing of a circuit and a schematic diagram of the circuits. First of all, let's talk about what a circuit is. So a circuit is very simple. It's just a pathway. It's a pathway through which current can flow. And when I say current, right, I'm referring to specifically electrical current. Okay? Circuits can be used to power objects, so they are used to control electrical current. Now, this diagram over on the left here, I'll label it diagram A. Right? It's a drawing of the circuit. So what this drawing is that it's actually looking at what is in real life and drawing it. So you can recognize these look like batteries, right? And these look like light bulbs. But if you think about it, in reality, circuits can get very, very complicated. Because imagine trying to draw out the circuit of an entire house using drawings like this to represent what you see, right? That would be quite the burden to draw. So instead what's done is electricians and electrical engineers and all the scientists in the electrical field came up with this idea of schematic diagrams, where they use purposeful pre-assigned symbols to represent things you would see in a real circuit so that it's easier and much more practical way of drawing circuits. Okay, so in this diagram here, we're going to talk about these symbols later, but we can see that there are how many cells? Okay, you can pause the video and guess, but if we look here, we see one cell here, two cells, and three cells, so corresponding to each of these. So it's a bit of a misnomer. We, like everyday English, we call these batteries. Oops. But they're not batteries. Technically speaking, they are cells. Okay? And they're each represented by one of these. This whole thing together, connected here, technically speaking, that's your battery. Okay? So that means that this whole thing here is a battery that is made up of three cells. Okay? Each of these are resistors. So resistors will impede the flow of current. So in this simple diagram, we have three cells hooked up to a conductor. This black wire here is just a conductor that's hooked up to three resistors. Okay? We'll talk about the symbols in a second. Okay? Now, the most economical way to connect all the components in a circuit is just a simple loop. So if we have this, here's the simplest circuit you'll ever see. There's one cell, a conductor back to the other end of the cell. That is a simple circuit. It's not drawn very well. Let me redraw that for you. Right, that's better. Right, there you go. Okay, so that's an example of a simple cell there, or a simple circuit. Okay, so here's a very interesting scenario that we can run ourselves into. Maybe many of you have had experience with this already, but here we have Christmas lights, and the way Christmas lights are hooked up is each bulb is connected to another one in a one right after the other type of fashion. Okay, the wire then is connected to a voltage supply and a switch, and when the voltage supply is connected and the switch is turned on, then all the lights turn on. However, what is the problem with that? Okay, the problem is, if you haven't had this experience, is that when one light bulb is either disconnected or if it burns out, then all of the working bulbs will turn off as well, because the way electricity works is that it has to go through a loop, and the current has to pass through everything in the circuit. So if there's any interruption, for example, a disconnected or a burnt out light bulb, then current stops flowing. And if current stops flowing, then things do not function. So what would that look like? Every single light bulb would turn off. It's not that they're not working, it's just that one bulb that's defective stops the flow of current because it limits the pathway for current to flow. Okay, so all circuits have four important parts. Okay, so there are four important parts to a circuit. Okay, number one, source. There has to be a source of voltage. Okay, a source of energy. Okay, there has to be a conductor. A conductor will allow for the flow of electricity, electrical current. And lastly, well, not lastly, but there's something called a switching mechanism that will help control flow. And loads are, it's a fancy word for, or technical word for anything that you turn on. Like, I know I say turn on, it's kind of funny because the switching mechanism is what's turned on, like is what does the turning on and the turning off, but what is turned on or off is the load. So a load is, I think of it as anything that you want to function, right? It's the purpose of the electrical circuit. So an example of a load could be your computer, right? Another example of a load, the most example that I'll be using in this class is a light bulb, right? That's the most significant example. Like, you know, another example would be a toaster, right? Your cell phone, right? Etc. Your PlayStation, your washer, your dryer, your anything that you can turn on, anything that you put into a circuit because you need to use it. That is what a load is. Okay. So again, four parts: sources, right? Again, here's the schematic symbol for a source, right? That is one cell. Anything more than one cell is called a battery. Conductor is usually given by this, right? Just a straight line. Switching mechanism, right, is given by this symbol, right? We put one dot there and another dot there, and oops, we would say that this switch is open, okay? And in the open configuration, nothing would work, right? Because the pathway for the electrons to flow is interrupted. And then you have this configuration of a switch, right? Meaning that the switch is closed, and that means that the current is flowing and the device will function. Sources of energy, sources of specifically electrical energy, will provide the energy for a circuit. It says here a supply of electrons for the circuit, but it doesn't supply the electrons. Okay, that's incorrect. Okay, it's not a supply of electrons because electrons are already in the conductor. So the battery, for example, or the cell, I should say, will not provide electrons. It will provide the push for those electrons. Okay, so these are three examples of sources of energy. Here we have a nuclear power plant that will convert nuclear energy to electrical energy. Okay, in the second picture here we have a battery that we typically call every single day in our normal English, but this is a cell, hence the name Duracell, and it converts chemical energy to electrical energy. Okay, and this is a generator. So this generator, here you can see the motor right here that I've X'd for you. This takes kinetic energy, the energy of motion, and converts it into electrical energy. Okay, so how this works is, you know, we'll talk about it later, but essentially you have a coil rotating in a magnetic field, and that will generate electricity. Conductors provide the path for current. Wires are drawn as straight lines in schematic diagrams. Here are some examples of conductors. Switching mechanisms will control the current flow. You can turn it on, turn it off, and directs it into different parts of the circuit. And the load, of course, the load will convert electrical energy into some other form of energy, right? I think of it as something that you would just turn on in a circuit, right? So for example, a light bulb will convert that electrical energy into two different forms of energy, into light energy and heat energy. Okay, so here's another slide for you, and this just shows what a schematic diagram would look like. And again, here we have a battery. Why do we call it a battery? Because how many cells do we have? We have two cells. Okay, our long part here is the negative pole, and this is the positive pole, negative and positive, and electricity flows from the negative pole to the positive pole. So each of these schematic diagram, like this schematic diagram shows some schematic symbols. A resistor you'll see as a waving line like this. Conductor is just a solid straight line. A circle with an A in it means an ammeter. And can you guess what an ammeter does? An ammeter will measure current, okay? Because it's an ammeter and current is measured in amps. Hence, the ammeter will measure the amount of electrical current in a circuit. And here you have a switch. Okay. Okay, so here I have a simple diagram, schematic diagram labeled for you or drawn for you. Here we have two cells, okay, hooked up to a light bulb, a load that's hooked up to a switch. Now, you are responsible for understanding how to analyze circuits. And so analyzing circuits is easy to do if you just, well, it takes practice, but it'll help you. What will help you to do this is something called finger tracing, right? So you just, all that is just using your finger to trace the pathway of electrons. So you start by labeling the poles of your cells, right? So this will be our negative pole, this will be our positive pole, and then you take your finger, right? I don't know if you can see that little white circle here, but you take your finger and you just kind of follow the path of electrons. So here it would stop, right? It would stop because this switch is open, right? And so if the current stops here, it can't go through and can't go through the conductor, through the load, back to the positive end. And because it can't complete that loop, this light here will not be turned on. However, if we take the switch and we close it, right? So if we close it, if we do something like this, we'll close the switch, right? Imagine that. And then we trace our pathway of electrons from our negative pole. We go, oh yeah, all the way, there you go. So then we can see that that light bulb will turn on because the electrons can make it right back to that positive pole. So it's all about going there and back again. Okay? Use the technique of finger tracing. No, it's not very nicely written, but there you go. Okay, so let's talk about what a series circuit is. I mentioned it in the last slide, but a series circuit is just when loads and components of circuits are hooked up one right after the other. Okay, so one component is connected to another in a one right after the other fashion. Right, in one after the other type of fashion. Okay, that's what a series circuit is. Okay, that's what a series circuit is. So if we take that, we can draw one really quick, and we can show you what a series circuit is. The circuit from the previous slide, that was a series circuit. Okay, so here's an example of a series circuit that I have drawn for you. So here we have, again, our cell. We have two cells there, our battery. Here's our negative pole and our positive pole. Okay, and we have three loads. Actually, we have four loads, but we have 1, 2, 3 light bulbs, and we have one voltmeter. So a circle with a V is a voltmeter. Okay, and that is something that will measure voltage. So again, if we finger trace, okay, and we ask ourselves a question, if I turn this switch on, will light bulb A turn on? Will light bulb B turn on? Will light bulb C turn on? Or will one turn on and the others won't? What's going to happen? Well, if we turn our switch on, okay, and we follow the path of electrons, we see that there's a path here, and the electron's going to cut through our voltmeter, or pass through our voltmeter, so we'll be able to measure the voltage. And it passes through this light bulb, this light bulb, and the first light bulb, and goes back to the positive. So this switch here is a master switch. It controls current to the whole circuit. Therefore, this switch will control if light bulb A, B, and C light on. Okay, that's in a series circuit. A parallel circuit is a little bit different, so we'll talk about that right now. In a parallel circuit, as you can see, there's more than one path. There's more than one path for current to flow. Okay, so this is where analysis can be a little bit tricky, but this is the way to do it. So again, we start off with labeling our negative poles and our positive poles. Okay, and we go ahead and we trace our electrons. Okay, so we'll look at, we'll call first, before we do that, just let me label each of these light bulbs as A, B, C, and D. Okay, so we can ask ourselves some questions. So which light bulbs will turn on if I close this first switch? So if I close this first switch, right, like this, okay, which light bulb, and I leave this switch open, which light bulbs will turn on and which ones will not? So how do we answer this? Well, we have to do some finger tracing, okay? So we just start up right here, okay, and we follow the flow of electrons, goes through here, we'll go through here, okay, and now see this is where it's a parallel circuit, right? So the electrons will go down, but here's another path. So some will go down this way, and electrons will also go down this way, or off through this light bulb. So we'll follow this path first, okay, and then it goes back here, and because it completes the circuit, if we close the switch, light bulb A will turn on. Okay. Okay, if we follow some more electrons, goes down, it can go through light bulb B and back up over here, thereby completing the circuit. So this switch controls light bulb A and light bulb B. If we do the same thing, go all the way down, we cut through C. Okay, there we go. That means C will turn on. So this switch controls flow to A, B, and C. Let's try again. Let's go all the way down to D. Oh, well, what happens here? This switch is open. So if that switch is open, that means current cannot pass through. Oops, current cannot pass through here. So that means if we turn this switch on by closing it, A, B, and C will light on because each pathway will provide electrons a way to get back to that battery, back to that battery, the positive end of it. And I call it a battery because we have more than one cell. Okay, but this switch is open, so no electrical current can flow through here, and this light bulb therefore will not turn on. So this switch controls light or electrical current to A, B, and C, but this switch, right, controls current to D and D only. Because if this switch is open, it doesn't matter. Electricity can still flow through A, B, and C provided that this one is closed. But this one has to be closed for these. Sorry, both of these switches have to be closed in order for electrical current to pass through D. So if you do the tracing again from here, it goes all the way down. Both switches are closed, so electrical current can flow through that light bulb back to the positive terminus. There you go. You have a complete circuit. So that's the circuit analysis for this circuit, this parallel circuit. So it's called parallel because each of these loads are hooked up in parallel to each other. Okay. Within this circuit, I should say there is a series circuit as well, because we have this end connected here right after the other. There is a series, there is a series, there is a series circuit, but in parallel, it's these loads that are hooked up to each other in parallel. Okay. A combination circuit is just that. We've got series and parallel mixed in. So here's our combination circuit. Again, finger tracing. We start with the negative, labeling our negative and positive terminals, sorry, and we go ahead and we finger trace it, right? So again, we close our circuit here, we open our switch, okay, and we notice that There's the pathways open for every single one of these light bulbs. There's our first path coming right back through A, so both of those will turn on. Then we find that the same thing happens when the circuit goes through C. Therefore, this is the master switch controlling light bulbs A, B, and C. Okay, so for example, if we were to throw a switch here, right, in this part of the circuit, well, that would control electrical flow for C. So then this switch would have to be closed for C to work and open for C to not work. Okay, so just comparing series and parallel, you do need to know this. This is an important distinction. In a series circuit, if the pathway is interrupted in any way, the whole circuit cannot function, just like the Christmas lights we talked about. Adding components increases the total resistance of the circuit. Okay, this is important. I'll talk about this in a second. This means that adding an extra bulb to a string of lights makes all of the bulbs dimmer. Okay? In a parallel circuit, any interruption or break in one pathway does not affect the rest of the pathways in the circuit because there are multiple pathways for which the current to flow through, thereby allowing other loads to function just well if there's any other break or interruption. Adding a new pathway does not affect resistance in other pathways. In fact, adding extra resistors decreases the total resistance of the circuit. Okay, so now I'm going to show you one thing that you do need to know and one thing you don't need to know for our purposes, but you will need to know this again in high school, I do believe. So if we were to calculate, if I were to give you a circuit and I wanted you to find the voltage and I give you the current and I give you a series of resistors, well, you'd have to calculate the total resistance to get the resistance to plug back into the Ohm's law equation to find out what the voltage is. And in the parallel circuit, the total resistance, R is for resistance, T is for total, is equal to the resistance of one resistor plus the resistance of the other resistor plus however number of resistors you have. Okay? So there's a series right there. You don't have to know this part, but the resistance in the parallel circuit decreases. Okay, that part you do need to know. Okay, so adding more resistors in a parallel circuit actually decreases the total resistance. Here's the mathematical formula that shows you why. Okay, and that formula is, where is it? Oh, sorry, right there. 1 over the total resistance. So the inverse of total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R to the n, so how many resistors you have there. So you can see that the inverse of the resistance is going to be less. You don't have to know this formula, okay? But do understand that in a parallel circuit, if you add more resistance, it's going to decrease, more resistors will decrease the total resistance of a circuit, okay? So here's an analogy as to why. Maybe this will help you understand. Resistance is impedance to flow. The more paths there are in a circuit for electricity to flow, the less resistance there is in the overall circuit, okay? Because there's more than one path for the current to flow. Think of it like straws in a glass of your favorite strawberry milkshake or chocolate milkshake. There are multiple paths for the chocolate milkshake to leave the glass, right? And so because there are multiple paths there, right, well, the resistance is decreased, right, because you have more than one possible path for the chocolate milk to escape. Here you only have one path, so this has more resistance than this one. Hopefully that helps a little bit understanding why. So series circuits, they do have an important use. They are used in house circuitry. However, parallels used a little bit more. Switches are wired in a series with other components, wall plugs and lights, which makes it possible to turn off all the electricity in the circuit. So for switches, they're hooked up in series to the loads. As I was saying, household wiring is one of the many applications that use parallel circuits. Okay, so parallel circuits are used in your home. And it's very important because let's say if you are doing your online learning, your distance learning on your laptop that's hooked up, plugged into your 120-volt outlet, and upstairs your mom or your dad or your uncle, your aunt turns on the light, and for whatever reason they turn on the light bulb pops, it goes up, it stops working, right? It burns out. Well, if your wiring in your home was in series, then your laptop would turn off too. Okay, so you wouldn't want your refrigerator to go off if a bulb burned out. Okay, thanks for your patience with this. I know this is a longer one, but we're doing a lot here, so it's okay. So this is what a switch would look like in your home. Of course, we all have experience with that. Um, but so far, we've been talking about circuits that are large. Okay, so for example, circuits that are involved in the workings of your home. Okay, that's a macro circuit. But there are microcircuits. Okay, so these are examples. The circuits that would work in your, for example, your cell phone. Okay, the cell phone circuitry is not large, and it's not the size of the wiring that's involved in your home. Okay, but it works the same way essentially. Okay. So, for example, regular switches are practical and convenient for your home, but how do switches look like in tiny circuits? Well, they look like this, and they're called different things. They're called transistors. Okay, so a transistor is one of these things, pretty much, but for a much smaller circuit, a circuit found in your cell phone, for example. Okay, transistors do other things, but I'm not going to talk about that right now. For our purposes, we need to know that transistors are switches that will turn things on and off in a microcircuit. Okay, so transistors can be solid state. Meaning that they're made of solid material with no moving parts. Okay, most are made with 3 layers of specially treated silicon, and we learned that silicon is an element that we find on the periodic table on the staircase. So it exhibits properties of conductors and insulators. So it's very important uh, element that's used in microcircuits. Okay, in your computer, for example. A small voltage through the middle layer controls a current between the outer layers, and this way transistors can act as switches. Okay, so that's just how they work. So microcircuits, this is a really nice picture of a microcircuit. They're made up of microscopic transistors and resistors. So we see transistors and resistors in here. There are circuits on extremely small scales, and people who work on microelectronics need to look at these circuits under a magnifying glass. And latest microcircuits contain more than 1 million components in a square centimeter, so it's quite sophisticated.